Hello there. Today, we're going to explore a classic puzzle from the world of computer science that, believe it or not, has a whole lot to say about the choices you and I make every single day.
You know that feeling, right? When you're packing for a trip, your suitcase is just about to burst, and you have to decide what you absolutely can't leave behind. Or maybe you're at the grocery store, and you've only got so much cash on you. That feeling of weighing your options, knowing you just can't have it all.
Well, it turns out that this totally universal experience, this little dance we all do between what we want and what we can actually have, it has a formal name. It's called the knapsack problem. So let's start with the classic story that gives the problem its name. It's a scenario that makes the whole idea click into place almost instantly. Okay, picture this, a thief with a knapsack. The store is filled with all sorts of treasures. Each one has a certain weight, and each one has a certain value. The problem is, the knapsack can only hold so much. So the thief's puzzle is, which combination of items gets them the most value without ripping the bag? So really, we're juggling three things. A bunch of items, each with its own value and weight, a container with a hard limit, and a goal to squeeze out the maximum possible value. It's a puzzle about making the best of what you've got. All right, now this is where it gets really interesting. Because this one puzzle actually splits into two different versions, and that little difference between them changes absolutely everything. On one side, you have the fractional knapsack problem. This is where you can take just a piece of an item. You can think of it like scooping up gold dust. You can take exactly as much as you want. But on the other side, you've got the 0 or 1 knapsack problem. And here, it's all or nothing. You either take the whole thing or you leave it. Think of these like solid gold ingots. You can't just snap a piece off. Let's look at that first version, the easier one, and see how you might solve it. It turns out there's a really intuitive and kind of beautiful way to approach it. So for the gold dust problem, the fractional one, the best way to go is what's called a greedy strategy. And it's called greedy because, well, at every single step, you just make the choice that looks the absolute best in that one moment. Here's how it works. First, you figure out the bang for your buck for every single item, its value per pound. Then, you just start taking as much as you possibly can of the item with the highest value per pound. When you run out of that, or your bag is getting full, you just move on to the next most valuable item. And you keep going like that until the knapsack is packed. And here's the cool part. For this version of the problem, this simple, greedy strategy is perfect. It will always give you the maximum possible value. It's guaranteed to be the best solution. And just take a moment with that. Isn't it kind of nice when a problem that sounds complicated has such a simple, clean answer? There's just a real satisfaction in that. But you probably saw this coming. Things don't always stay that simple. Let's switch over to that other version of the problem, where one little change makes a huge difference. What happens when we can't take little bits and pieces? What happens when we're dealing with those gold ingots, where it's a take it or leave it kind of choice for every single item? Well, that one little rule, that all or nothing rule, causes our beautiful, simple, greedy strategy to completely fall apart. The choice that looks best right now can actually lead to a worse outcome in the long run. And this table shows us exactly how that can happen. Let's say our knapsack holds 50 pounds. Item 1 has the best value per pound, so the greedy choice is to grab it. After that, we have room for item 3, giving us a total value of $180. But look at the optimal choice. It actually skips that best item and instead takes items 2 and 3. That fills the knapsack perfectly and gives us a way higher value of $220. See? By grabbing the most tempting thing first, we accidentally blocked ourselves from getting the best overall result. Let that sink in for a second. This is so much more than a puzzle about algorithms. It's a quiet little reminder that sometimes the most appealing choice in the short term isn't the one that gets us where we really want to go. So, why does any of this matter if you're not in a computer science class? Well, because this whole idea gives us a really powerful way to think about our own limited resources. Look, you don't need to be doing complicated math in your head all day. The real takeaway here is just having a mental model. It's a new lens to see the decisions you're already making every day. Think about it like this. Your knapsack could be your time or your budget, or even just your energy for the day. And the items? Those are all the things you could do. Projects for work, chores, hobbies, hanging out with friends. Each one has a value, how important it is to you, and a weight, how much time or energy it costs. What the knapsack problem really teaches us is that every time we say yes to something, we're also saying no to something else. When you choose to spend your energy on one thing, that's energy you can't spend on another. It makes those hidden trade-offs visible.
And maybe that's the real lesson here. We're probably not gonna find the one perfect, optimal solution for our lives. But by thinking in knapsacks, we can learn to make our choices a little more consciously, a little more thoughtfully, and with a clear idea of what really and truly matters to us.